A whiteout storm swallows the horizon. Winds scream across frozen terrain. Temperatures plunge far below zero. Visibility collapses to almost nothing. Most vehicles would surrender. These machines accelerate. Welcome to the era of compact snow monsters, precision-engineered winter vehicles designed not just to survive extreme conditions, but to rule them. At first glance, they appear deceptively small. Low-slung chassis, aggressive stance, reinforced microtracks or hybrid studded snow tires, lightweight composite frames engineered to remain rigid even in punishing cold. But size is the illusion. Underneath that compact shell lies something far more strategic. Advanced torque vectoring systems distribute power independently to each track or wheel. AI-assisted traction control reads ice density in real time. Suspension geometry automatically adapts to uneven frozen terrain, lifting, compressing, stabilizing before instability even occurs. This isn't brute force. This is calculated winter dominance. Imagine a frozen mountain pass at dusk. The wind cuts through steel like a blade. Ice crystals scatter across the surface, forming unpredictable friction patterns. A conventional SUV hesitates. A compact snow monster reads the terrain through embedded surface sensors, adjusting grip pressure by milliseconds. Power flows where it's needed. Stability remains unwavering. Blizzards don't intimidate it. They activate it. Engineers designing these machines focus on three pillars: traction, resilience, and intelligence. Traction begins with ground contact. Micro-pattern track surfaces are layered with cold-resistant polymers that remain flexible at temperatures where rubber would harden and crack. Some prototypes incorporate retractable ice studs that deploy automatically when surface hardness thresholds are detected. Resilience comes from materials science. Aerospace-grade aluminum alloys blended with carbon composites resist structural fatigue caused by rapid temperature shifts. Critical components are insulated against frost penetration. Battery systems use thermoregulation chambers that recycle excess motor heat to maintain optimal performance in sub-zero conditions. But intelligence is the real weapon. Embedded neural processors analyze wind resistance, incline gradients, snow density, and thermal drift, all simultaneously. Instead of reacting to danger, these machines predict it. On open tundra, where snowdrifts conceal hidden drops and ice plates fracture without warning, predictive mapping systems scan the surface using ground-penetrating radar and forward-facing LiDAR. What looks like chaos to the human eye becomes data, and data becomes advantage. Now imagine urban winter warfare. Icy city streets locked in gridlock after a historic storm. Emergency response teams struggle to move through blocked roads. Compact snow monsters weave through narrow alleys, climb snowbanks, and navigate terrain traditional rescue vehicles can't approach. Their small footprint becomes their superpower. But performance alone doesn't create dominance. Endurance does. During prolonged blizzards, fuel efficiency or battery optimization becomes critical. Some models integrate hybrid microturbine generators that recharge electric systems while operating. Others rely on ultra-dense battery packs insulated by vacuum-sealed thermal chambers. The result? Sustained operation in conditions that drain conventional vehicles within hours. Inside the cockpit, the driver isn't wrestling with chaos. They're commanding a controlled system. Heated panoramic glass prevents ice buildup. Heads-up displays project terrain overlays. Real-time diagnostics ensure every component operates within ideal thresholds. Outside, the storm roars. Inside, control remains absolute. And this shift from survival to dominance changes everything. Winter is no longer an obstacle to mobility. It becomes a domain. As these compact snow monsters evolve, they begin integrating swarm coordination capabilities. Multiple units communicate wirelessly, sharing terrain data instantly. If one vehicle detects thin ice or unstable snowpack, the entire fleet adjusts its route. The machines learn collectively. The frontier expands. Military strategists analyze their mobility potential in Arctic operations. Disaster relief agencies evaluate their efficiency in avalanche zones. Remote research teams consider them lifelines in polar expeditions. Because when mobility becomes reliable in the harshest climates on Earth, geography loses its power to isolate. But innovation never stands still. Engineers are already experimenting with adaptive track morphing, surfaces that physically alter their pattern depending on snow type. Phase change materials embedded in the chassis absorb shock energy during sudden impacts. Autonomous navigation systems refine themselves with every storm encountered. Each iteration shrinks size and increases capability. And somewhere beyond the next blizzard, beyond the next frozen mountain ridge, the next generation waits in development labs, leaner, smarter, even more ruthless against winter's unpredictability. The storm clouds gather again. Winds accelerate. Snow begins to fall thicker. And out on the horizon, a small silhouette moves forward, undeterred, not surviving. Because the real transformation hasn't even revealed itself yet. What happens when these compact snow monsters stop being manually commanded and begin operating fully, autonomously? Imagine a remote Arctic research station cut off after a catastrophic storm. Satellite signals flicker. Supply lines are buried beneath meters of compacted snow. Temperatures drop to levels that freeze exposed steel within minutes. No human driver steps into the storm. Instead, a fleet deploys automatically. Engines hum to life inside insulated hangars. Navigation systems sync with orbital weather feeds. Terrain models update in real time as LiDAR scans the shifting landscape. And then, they move. No hesitation. No fear. No fatigue. Autonomous winter machines carving precise paths through blinding whiteout conditions, adjusting traction microseconds before encountering black ice hidden beneath powder layers. Where a human might misjudge visibility, these systems rely on thermal mapping. Where a driver might panic under zero visibility, these vehicles calculate probability vectors. The storm becomes mathematics. And mathematics rarely loses. But dominance in extreme winter environments is not just about reaching a destination. It's about rewriting what access means. Entire regions of the world remain economically limited by seasonal isolation. Mountain communities cut off for weeks. Arctic corridors deemed too volatile for consistent logistics. Emergency evacuations delayed because traditional vehicles cannot safely traverse unstable snowpack. Now imagine compact snow monsters operating as winter infrastructure. Regular supply routes maintained regardless of blizzard intensity. Remote villages connected year-round. Medical response times reduced from hours to minutes, even during historic storms. When mobility becomes independent of weather, winter stops dictating human limits. And the engineering doesn't stop at land. Hybrid variants are already being conceptualized. Machines capable of transitioning from snow to thin ice, distributing weight dynamically to prevent surface fracture. Others experiment with amphibious cold weather capability, allowing seamless passage from frozen shoreline to partially thawed water channels. Adaptability becomes survival. Survival becomes supremacy. But perhaps the most revolutionary evolution lies in energy autonomy. Future models integrate kinetic recovery systems designed specifically for snow terrain. Every microslip, every downhill descent, every track rotation feeds energy back into the power system. Combined with high-efficiency thermal recycling, these vehicles begin to approach extended off-grid endurance. Weeks, not days. Storm cycles, not hours. A machine that can operate independently through multiple blizzards without external resupply is no longer just a vehicle. It's a strategic asset. And then comes the psychological shift. For centuries, winter has symbolized limitation. Travel postponed. Plans delayed. Movement restricted. But when compact snow monsters glide through storms as if navigating calm pavement, perception changes. The storm is no longer feared. It's studied, used, even leveraged. Snowdrifts become natural cover. Frozen terrain becomes high-speed pathways. Harsh conditions become tactical advantage. And with each deployment, each successful mission across impossible terrain, the myth of winter invincibility fades. Yet there's something even more profound unfolding behind the scenes. These machines are teaching engineers how to design for extremes. Materials tested at -50 degrees inspire aerospace insulation. AI stability algorithms refined on ice influence urban autonomous driving systems. Traction models inform robotics operating in disaster zones. The innovation spills outward. What began as a solution for snow becomes a blueprint for resilience everywhere. And somewhere in a windswept testing ground, under skies heavy with incoming storm clouds, the latest prototype idles silently. Smaller than its predecessors. More intelligent. More adaptive. Engineers stand back, watching telemetry streams stabilize in real time. The storm front approaches rapidly. Wind speeds rising, visibility collapsing. The perfect test. The prototype engages forward motion. Snow blasts against its reinforced frame. Sensors flare to life. Traction calibrates. Navigation vectors shift dynamically as terrain changes beneath fresh accumulation. It doesn't slow. It doesn't falter. It advances, calculated, precise, relentless. Because these compact snow monsters were never built to wait for better weather. They were built to redefine what impossible looks like. And as the storm intensifies, as white swallows sky and ground into a single endless void, the silhouette keeps moving forward. Steady. Controlled. Because evolution in extreme engineering never pauses. Beyond the current prototypes, beyond the fleets already mastering frozen terrain, a deeper transformation is taking shape, one that blurs the line between vehicle and ecosystem. Imagine compact snow monsters that don't just respond to the environment, but actively reshape it. Advanced surface compaction systems begin optimizing snow paths as they travel, reinforcing safe corridors for following units. Microheating elements embedded within the track edges subtly stabilize dangerous ice sheets, reducing fracture risk without compromising structural integrity. Each pass through the storm leaves behind something greater than a trail. It leaves behind infrastructure. Now scale that concept. Entire Arctic transport lanes maintained by autonomous winter fleets. Supply corridors mapped and reinforced in real time. Avalanche-prone slopes monitored continuously by sensor arrays mounted on mobile units. These machines stop being reactive tools. They become environmental managers. But the true frontier lies in intelligence convergence. Future iterations integrate satellite swarm data, atmospheric pressure modeling, and quantum-accelerated forecasting engines. Instead of responding to blizzards as they happen, compact snow monsters reposition before impact, anticipating storm direction shifts hours in advance. They don't drive into storms blindly. They dance around them. And when confrontation is unavoidable, they adjust formation dynamically, redistributing fleet density to maximize traction redundancy and minimize exposure risk. A single vehicle is powerful. A synchronized network is unstoppable. Meanwhile, energy systems continue evolving. Engineers experiment with crystalline battery matrices engineered specifically for low-temperature conductivity. Internal heat exchangers become more efficient, capturing even microscopic thermal variance. Some prototypes explore hydrogen microcell integration, clean, high-density energy storage resistant to cold-induced performance drops. The objective? Total independence. A vehicle that requires no grid, no refueling station, no seasonal downtime, just movement. And then comes adaptability beyond snow. Designers begin testing modular chassis systems, interchangeable undercarriages capable of transitioning from snow tracks to tundra terrain modules within hours. The same compact machine that dominates blizzards becomes equally effective across rocky permafrost or slush-laden thaw zones. Winter is no longer a season. It's a spectrum, and these machines operate across all of it. Inside research labs, simulations grow more extreme. Wind speeds surpass recorded historical highs. Ice densities fluctuate unpredictably. Multi-layer snow collapse scenarios push structural tolerance to theoretical limits. Each successful test expands the boundary of what mobility means. Because this isn't just about vehicles anymore. It's about rewriting environmental constraints. Picture a future polar city, sustainable, energy efficient, thriving year-round. Logistics runs smoothly regardless of storm severity. Emergency response is instantaneous. Exploration missions extend deeper into once inaccessible regions, all supported by fleets of compact snow monsters working silently in the background. Invisible guardians of mobility. Yet the most profound shift may be psychological. When technology masters the harshest climates on Earth, humanity's perception of limitation changes. Engineers grow bolder. Architects design in colder zones. Scientists push further into unexplored regions. The presence of reliable winter dominance unlocks ambition, and ambition drives innovation even further. Out on a frozen expanse, beneath aurora-lit skies shimmering across the horizon, the newest generation prototype pauses briefly. Not from weakness, from calculation. Sensors analyze snow crystallization patterns mid-fall. Wind vectors recalibrate. Internal systems redistribute torque preemptively. Then, it accelerates again, slicing through layers of fresh accumulation as if the storm itself is cooperating. This isn't brute conquest. It's harmony through precision. A machine designed not to fight winter blindly, but to understand it so completely that resistance becomes irrelevant. And as the storm rages harder, as darkness settles across the frozen world, the compact silhouette remains in motion, quiet, efficient, relentless, because somewhere ahead lies terrain no machine has yet crossed. Beyond that horizon, engineers are no longer just thinking about vehicles. They are thinking about climate intelligence systems on wheels. Because once a machine can survive and dominate the most volatile winter environments on Earth, the next logical step isn't just endurance, it's awareness. Future compact snow monsters won't simply analyze terrain beneath them. They'll analyze atmospheric chemistry, ice density composition, magnetic field fluctuations, and subsurface instability patterns, all simultaneously. Imagine this. A vehicle approaches what appears to be solid frozen ground. But deep beneath the surface, shifting pressure layers suggest a hidden fracture zone forming. Traditional sensors might miss it. A human eye definitely would. These machines won't. They'll reroute instantly, milliseconds before the ice destabilizes. Not because they reacted, but because they predicted. And prediction is the ultimate form of dominance. Now picture coordinated fleets stretching across vast polar regions, acting like a distributed neural network. Each unit gathers environmental data. Each transmits insights. Each learns from the others in real time. Over time, the Arctic itself becomes mapped not just geographically, but behaviorally. Storm personalities, ice temperament, snow compression patterns unique to specific regions. The environment stops being chaos. It becomes a dataset. And once the dataset is understood, the concept of impossible weather dissolves. But the evolution doesn't stop at physical terrain. Communication systems embedded within these compact snow monsters could create emergency mesh networks during severe storms, providing temporary connectivity when traditional infrastructure collapses. Satellite interference? No problem. Cell towers down? Irrelevant. The fleet becomes the network. In disaster scenarios, that capability alone could save thousands of lives. And then comes modular intelligence. Engineers are exploring AI cores that can be upgraded without replacing the entire vehicle. Imagine swapping an enhanced navigation cognition like installing a new brain, instantly elevating the fleet's collective capability. A machine purchased today could evolve dramatically over the next decade. Growing smarter, more efficient, more resilient. This isn't planned obsolescence. It's continuous evolution. Now think bigger. What happens when compact snow monster technology begins influencing extraterrestrial mobility design? Because the same systems engineered to conquer Earth's harshest winters are shockingly similar to what would be required on icy moons or frozen planetary surfaces. Extreme cold, unstable terrain, limited visibility, autonomous survival. The line between Arctic innovation and interplanetary exploration begins to blur. And suddenly, the storm you see raging across frozen tundra doesn't just represent winter. It represents preparation. Preparation for harsher environments. Preparation for deeper exploration. Preparation for frontiers beyond Earth. Back on that frozen plain, the prototype pushes further into uncharted white silence. Its tracks leave geometric precision across chaotic snowdrifts. Wind howls at ferocious speeds. Visibility drops to near zero. Yet telemetry remains stable. Internal systems hum with calculated confidence. Because these machines were not built to fear the storm. They were built to study it, to adapt within it, to move through it as if it were simply another equation to solve. And somewhere inside research facilities illuminated by cold blue light, engineers are already analyzing performance logs from this very mission. They see efficiency gains, microtraction improvements, energy recovery spikes beyond projections. Each data point is a stepping stone towards something even more radical. Because the next generation won't just dominate blizzards. It may redefine mobility itself. Not seasonal, not regional, but absolute. A world where no climate dictates movement. Where no storm delays progress, where no frozen terrain remains unreachable. And as the storm intensifies one final time, snow swirling like a living entity attempting to reclaim control, the compact snow monster does something unexpected. It accelerates, not recklessly, not defiantly, but confidently, as if winter has already been understood, already been mastered, already been rewritten. And beyond the storm's edge, another horizon forms, and as that new horizon sharpens into view, something changes in the mission parameters. This is no longer a demonstration. It's a transition. Because once dominance over terrain becomes routine, the question shifts from can it survive to what else can it transform? Engineers begin integrating adaptive morphology, micro-adjustments in chassis geometry that subtly alter weight distribution depending on snow density. The vehicle doesn't just adapt through software anymore. It adapts physically. Panels contract to reduce drag in high winds. Suspension stiffens when detecting subsurface ice plates. Track tension recalibrates in real time to match crystallization levels of freshly fallen snow. The machine reshapes itself to fit the storm. And with each iteration, efficiency climbs. Energy reclamation systems harvest kinetic feedback from track vibration. Thermal gradients between interior and exterior surfaces are converted into microcharges. Even the force of crosswinds is partially redirected into auxiliary turbines. Movement becomes power. Resistance becomes fuel. Now imagine fleets of these compact snow monsters operating across remote energy sites, wind farms in polar regions, research installations buried beneath ice, mining operations in sub-zero climates. They don't just transport. They maintain. They repair. They construct. Autonomous tool arms extend from modular compartments. Drone units deploy from roof-mounted bays, scanning for structural weaknesses or incoming weather anomalies. The vehicle becomes a mobile operations center. And then, a breakthrough. Engineers test neural adaptive terrain learning, a system where the machine doesn't rely solely on preloaded data. Instead, it forms its own operational instincts over time. It remembers how a specific valley behaves during rapid temperature drops. It recalls how a certain ridge produces deceptive snowdrifts that conceal hard ice. It develops memory. Not human memory, but environmental memory. And that memory compounds with every mission. Over years of operation, a fleet becomes exponentially more intelligent than the day it was deployed. No reset. No stagnation. Just progression. Meanwhile, global interest grows. Defense agencies evaluate its mobility advantage. Climate researchers see a data goldmine. Explorers envision deeper polar expeditions without the traditional risks that once limited ambition. But perhaps the most radical application lies in humanitarian relief. When extreme winter storms cripple cities, roads frozen, infrastructure collapsed, these compact snow monsters could carve lifelines through chaos, delivering supplies, restoring communication nodes, evacuating stranded communities, operating where conventional vehicles fail within minutes. And all the while, refinement continues. Quantum-optimized route simulation shortens traversal time by fractions of a percent, then full percentages, then leaps beyond previous records entirely. Material scientists experiment with self-healing exterior composites capable of repairing microfractures caused by repeated ice impact. The vehicle not only survives damage, it corrects it. And then comes stealth efficiency. Acoustic dampening reduces operational noise to near silence. Infrared signatures are minimized through heat diffusion layers. In the stillness of a frozen night, the machine moves almost invisibly. A silent architect of mobility. Now return to that endless, white expanse. The storm begins to thin. Auroras ripple faintly overhead. Telemetry streams back to command centers thousands of miles away. Performance metrics exceed expectations again. But the most fascinating data point isn't speed, or torque, or endurance. It's stability. Despite escalating wind shifts and unpredictable ice layering, system variance remains nearly flat. The machine isn't fighting the environment. It's synchronized with it. And somewhere deep within its adaptive core, new parameters are forming, lessons from this journey being etched into digital instinct, preparing it for harsher trials ahead. Because this mission was never the final objective. It was a calibration, a stepping stone toward even more extreme conditions. Engineers are already designing Phase 2. Higher altitudes, lower temperatures, longer autonomous cycles without human oversight, and, eventually, permanent deployment. Self-sustaining winter fleets operating year-round without interruption. No off-season, no retreat, just continuous forward motion. And as the prototype crests another frozen ridge, scanning vast, untouched terrain beyond, the silence feels different. Not empty, but expectant. Because somewhere beyond that shimmering horizon, challenges greater than any storm are waiting. And these compact snow monsters, and then, after thousands of miles across ice fields, frozen valleys, and blizzard corridors, the realization becomes undeniable. This was never just about conquering winter. It was about redefining limits. The final test begins quietly. No dramatic announcement. No media spectacle. Just a fully autonomous deployment into the harshest recorded storm window of the season. Wind speeds spike beyond projections. Temperatures plummet past historical averages. Visibility collapses into white void. And yet, the compact snow monster does not hesitate. Sensors recalibrate. Thermal systems stabilize. Navigation intelligence shifts into predictive mode. Every previous mission, every dataset, every environmental memory accumulated over years now converges into this single moment. This is not reaction. This is mastery. Hours turn into days. No external intervention. No manual override. No rescue protocol required. When the storm finally weakens, satellite feeds reveal something extraordinary. Perfectly carved tracks stretching across what meteorologists had labeled non-traversable terrain. A silent signature of technological evolution. Back in the command center, there is no cheering. Only a quiet understanding. Mobility has changed. Winter is no longer an obstacle. It is an environment to operate within. The compact snow monsters that once seemed experimental are now inevitable. From polar research to disaster response. From remote infrastructure to future off-world exploration. From survival to supremacy. What began as a bold engineering concept has become a new category of machine, one that doesn't challenge nature, but harmonizes with it. And as the final telemetry logs close, engineers begin drafting designs for the next generation. Lighter, smarter, even more autonomous. Because innovation never stops at victory. It builds on it. The storm fades into the distance. The aurora flickers one last time above the frozen horizon. And the machine powers down, not in defeat, but in completion. The age of climate-dominated mobility is over.